Hi guys, and welcome to another video. This week we're going to be talking about patterns in data. But before we start this week, I just want to say well done for getting through last week with all the probability stuff. I know that you might not have found that easy. It was definitely quite a challenging week. So if you managed to get through that and you came away from it understanding a little bit more about probability, then that's great. If you felt that was okay, then you're going to be absolutely fine with the rest of the course. That's about as hard as it's going to get. So with that said, let's get into the topic of this week. And the first thing that I want to ask you guys is, have you ever stopped to think about how your brain processes the world around you? Now that might seem like a bit of a strange question. So I want to give you an example. If you load up YouTube and you see a picture of a video which has a cat on the thumbnail, how is it that your brain is able to recognize that as a picture of a cat and kind of, almost instantly? So you just look at the picture and then you kind of, within a fraction of a second, your brain is able to interpret that as a cat. What's actually going on in that process? Well, the first thing that happens is that the pixels representing the cat, which are on the screen, leave the screen in the form of light, and they enter your eyes, right? So you've got all these kind of photons of light, which are sort of in this shape of a cat, which are kind of leaving the screen, traveling through the air, and then entering your eyes. And then those photons of light are gonna hit the back of your eyes, hit your retina, where they're going to stimulate various nerve cells. And those nerve cells are going to send electrical impulses to your brain, which your brain is then going to perform some kind of neurological computation on and form this idea or sense of a cat. So that's actually a pretty complicated process, and it's pretty amazing that happens instantly. But you can kind of think of it, one way of thinking about it is that you're getting this kind of information, these patterns, in the form of light, in the form of pixels, which your brain is kind of interpreting. So you might see a line here and a line there, which then you kind of say, okay, that's forming a sort of triangle shape of an ear, and that's a sort of circle shape, which is forming an eye, and you put all of these sort of smaller patterns together and decide, okay, this is a cat. And that whole thing happens instantly, which is pretty amazing when you think about it. It's pretty incredible that our brains are able to process that much information and turn it into a coherent picture so fast. And if you think about kind of the informational content of that picture, well, that picture is made up of, so this one here, for example, is made up of 1,280 pixels by 720 pixels. So that's about 900,000 pixels. And then each one of those pixels is made up of a smaller red, green, and blue pixel. So you can multiply that whole thing by 3 to get almost 3 million tiny little pieces of information. So if you don't know, this is kind of how we store digital photos. It's basically just a list of numbers in each direction. So you've got a sort of rectangle photo, you've got a sort of rectangle of numbers, and at each position you've got 3 numbers, which represents the amount of green, red, and blue in that individual pixel. So the whole thing is basically, in this picture here, we've got 3 million little numbers, 3 million little intensities of light that are basically leaving the screen and entering your eyes. So what if we wanted to kind of teach a computer to do this process? Well, that is where data science steps in. Okay, so data science is basically the collection of techniques and algorithms that aim to make sense of huge amounts of data and discover the kind of patterns that are hidden within it, hopefully quickly and hopefully accurately. And data science as a field contains sort of a bunch of different subfields, including artificial intelligence, machine learning, statistical analysis. But all of these things are really just kind of more specific methods to do that, to kind of complete that same task, to make sense of huge amounts of data and discover patterns inside it. So how would we potentially go about writing a computer algorithm to kind of learn this kind of thing? So, we've just kind of seen that our brain is able to kind of process all of this information and decide whether this thing is a cat or a dog, I think is the example I'm giving. So we're trying to decide whether this picture is a cat or a dog. And we want to be able to teach a computer to do this kind of thing. So one of the things we often do is we give the computer lots and lots of examples. So we say, here is a ton of pictures of cats, and here's a ton of pictures of dogs, and can you start to work out the difference between them? And if you think about it, that's actually kind of similar to how we learn as humans, right? When we're babies, we don't have a preconceived idea of what a cat and a dog is, but we see a few examples, and then eventually we kind of work out the pattern. We work out what makes up a dog and what makes up a cat, what makes them different. So that's the kind of idea of what we're going to do with a computer. We're going to give it lots of examples of cats, lots of examples of dogs, and then we want to kind of see if the computer can learn the difference. But how is so about this kind of specific example of pictures, how is the computer going to actually see this data? Well, it's basically going to come in a big old table like this. So we're going to have an example. So this first one is going to be a cat, and we're going to have a picture associated with it. But that picture is just lots and lots and lots of little numbers, right, as we said before. So this is a cat. It's got a pixel, the sort of value at pixel 1. So this could be red at the top left. It's going to be 0.45. It's going to be green at the top left. It's going to be 0.23. And blue at the top left is going to be 0.38. Red at the top left but 1 is going to be this, and this is going to go on for ages and ages and ages and ages. This is going to be a big long list of 3 million numbers, where each one represents the pixel intensities. And then we're told, okay, that is a cat. So this is what the computer's going to see. And then we're going to give it another example, all of the pixel intensities again, and say this is a dog. And we're going to have a big long list of all these things, and we're going to say, okay, computer, from all of these millions of little numbers, can you start to work out what's a dog and what's a cat? So this is a pretty difficult task, and the kind of patterns that are hidden within this pixel information is going to be quite difficult to discern, potentially. But that's the idea, that's the task. So we're going to get there. We are going to eventually get to be able to discover these kind of really, really big hidden patterns inside of complex data. But to start off with, let's see if we can learn or start to think about a much simpler pattern. So let's consider a situation where we're not going to actually feed the data all of this kind of pixel information, all of these pictures of cats and dogs. We're just going to give it two numbers. We're going to say, this is an animal, and it has a weight of something, and it has a tail length of something. So we're just going to give it two numbers per example. So we're going to say this is a cat, it's got a weight of 6.6 kilograms and a tail length of 43 centimeters. Okay, that's one example. This is a dog, it's got a weight of 32 kilograms and a tail length of 31 centimeters, etc., etc. So instead of feeding it 3 million numbers per example, we're just going to give it two numbers per example. And in this case, they don't represent pixels, they represent actual physical measurements of this animal. But in essence, we've got exactly the same thing here. It's just our one's a lot more simple. We've got examples with numbers associated with them. So we're going to start to think about how we might be able to learn the kind of the class. So this is an example of a classification problem. So we've got two discrete classes, cat or dog, and we want to be able to tell the difference between them. So first of all, let's take a look at how we might want to plot this information. So one thing that we could plot here is we could basically have a sort of XY graph, and we could have the weight running along the bottom and the tail length running along the top, along the y-axis. And then we're going to plot a point for each one of our examples where the weight is the x value, or the sort of the kind of distance along the bottom, and the tail length is the height of that point. And then we can colour it in a different colour based on whether it's a dog or a cat. So hopefully this will make sense when we run this. So as usual, we're just going to do some imports here. We're just going to import matplotlib and numpy, and then these are some scripts that I've written. Okay, so we're going to make the first graph. So you can see here, this is an example of our data set where we've got the weight and the tail length for a bunch of different dogs and cats. And if it's a dog, we've coloured it blue, and if it's a cat, we've coloured it orange. So you can see just off the bat here that, dogs have a much bigger dispersion in weight. So we've got some tiny little pugs down here and some huge German Shepherds or St. Bernards, or that big mountain dog from Georgia that fights off bears. That'd probably be this one up here. And they have a big dispersion in tail length as well, whereas cats seem to be much more kind of centered around a weight. They sort of seem to have an average weight of about 5 kilograms and a tail length of about 45 kilograms ish. So this is an example of a data set, and you might be able to sort of start thinking about kind of rules that we could give to the computer straight off. We could say something like, okay, if we're trying to classify a new animal, so we don't actually know now if this is a dog or a cat, but we want to be able to tell just from its weight and its tail length whether it's possibly a dog or possibly a cat. We want to make a prediction. You could just say something like, okay, well, if the weight is between 2 kilograms and 10 kilograms, and the tail length is between 38 centimeters and 52 centimeters, then we'll say it's a cat, and otherwise we'll say it's a dog. So that could be an example of a really simple kind of rule that we could just apply. But the whole idea of data science and machine learning and artificial intelligence and all that is that we don't want to have to go through our data set and write out these rules. We want to be able to just learn these rules without having to do too much effort. So in this simple example, we might be able to come up with a kind of heuristic rule that just basically tells us what to guess if we get a new animal, but we don't want to do that all the time. So we're going to try and come up with a learning algorithm. And the learning algorithm that we're going to be talking about today is called 5 nearest neighbours. And the learning task can be stated pretty much like this. So given a new animal where we've measured its weight and its tail length, but we don't know whether it's a dog or a cat, can we predict whether this is a dog or a cat? And the way that this algorithm works goes basically like this. So the first thing we're going to do is plot all of the data that we've collected, so our labelled data where we know whether it's a dog or a cat. We're going to plot all of that on a big graph like this. So we've already done that. And then we're going to take this new point, so this new animal where we've been given its weight, we've been given its tail length, but we don't know the type of animal it is. We're going to take that as a point and plot it on the graph. So we're going to plot its weight and we're going to plot its tail length. So let's say this new animal had a weight of 20 and a tail length of 50, it would go up here. Or it had a weight of 50 and a tail length of 30, it would go here. So we're just going to plot that new point on the graph. And then what we're going to do is we are going to compare the distance of this, well, we're going to basically find the distance between this new point and every single other point on the graph. So we're going to literally measure the distance. You could think of sort of taking out a little ruler and putting it on your graph and measuring the distance from this new point to every single point, all of the dogs and all of the cats. And then we're going to basically find the 5 points that are closest to this new point. And if more of these points are dogs, so if more of them are blue, then we're going to say, okay, this point's probably a dog. And if more of them are orange, then we're going to say, okay, this new point is probably a cat. So that's the basic idea. And you'll notice that from this, we didn't actually have to ever specify any specific rules. We didn't have to say, okay, if it's between this weight and this weight, let's say it's a whatever. We just have the data, and it's a way of just telling from the data, we're able to sort of make a prediction. Okay, so we're just going to run this cell here, which should give you a decent idea of what's going on in this algorithm. So we've got all the data as plotted again, but we've plotted this new point here, which has a certain weight and certain tail length, and we can edit that. And you'll see that it's basically formed a line to the 5 nearest points. And as we kind of change that line, also change where that point occurs, you can see that it's connecting to different points. And as we go over here, you'll see that the point changes colour. So now it's orange because it's got more connections to cats than dogs. And we can change the tail length as well. You can see it's still orange. And then at a certain point, it becomes blue. So now it's closer to more blue points than orange points. So that's the idea of the algorithm. It's going to enable us to make a prediction. So you can have a play around with that and see if you can kind of understand that concept. Hopefully you can. So one thing that we're going to need to be able to do to run this algorithm is calculate the distance between points. Because as I said, when we plot this new point, we have to find the distance between all of the points in the graph and then find the 5 closest. So in this kind of plot here, we've only been sort of drawing the lines between the 5 closest. But in order to find out which 5 are closest, you're going to have to basically find the distance to all of the points on the graph. And the way that we're going to be able to find the distance between any 2 points on a graph is going to be to use Pythagoras Theorem. So you may have seen this at school. If you have, see if you can predict what's going to come next. Oh, it's a squared plus b squared equals c squared. So if we have a right-angled triangle and the base has a length of b and the height is a, then we can calculate the length of this hypotenuse here, the sort of diagonal, as a squared plus b squared equals c squared, which is the same as saying c is the square root of a squared plus b squared. But make sure this has to be a right-angled triangle. So this doesn't work for any triangle. It has to be a right-angled triangle here. So that's got to be a 90-degree angle at the bottom. Okay. So as I said here, you've got c squared equals a squared plus b squared. So c is the square root of a squared plus b squared. But we don't want to know the length of the hypotenuse of a triangle. We want to be able to calculate the distance between 2 points on a graph. But we can do that fairly easily. So if we had 1 point here at this top corner and 1 point here at this bottom corner, then the distance between those 2 points on this graph is going to be basically their x distance squared plus their y distance squared, and it's going to be the square root of those two things. And their x distance is basically going to be the x coordinate of this one minus the x coordinate of this one. So you could think if this was 0 here, then the x coordinate of this one would be this length, and the x coordinate of this one would be this whole length here, like that. So the difference between them is going to be this whole length minus this length here. And that's going to give us that length there. And the same for y. If this is 0 here, then the y height of this one is going to be all of that. The y height of this one here is going to be just this bit here. And the difference is just going to be all of this minus all of this. And that's what we've got here. So this formula is starting to get a bit more complicated, but hopefully you can still understand it. So the distance between a point at coordinates x1, y1 and coordinates x2, y2 is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. And one thing to note here is that it doesn't actually matter which order you do it in. So you could do x1 minus x2 squared or x2 minus x1 squared, and the same for y. It doesn't actually matter because if you do the subtraction in the other order, then it's just going to be the negative of whatever it was in the other order, in the original order. And when you square a negative, you just get back the same thing. So let me just do a real quick example here. So for example, if we did 5 minus 3 squared is 4, which is going to be the exact same thing as 3 minus 5 squared. It's 4. So the order here makes no difference. So that's nice. Okay, so just so that we can get that concept, I'm just going to run this graph here. So you can kind of have a play around with this. So we're basically going to be able to move the coordinates of this point. So here I'm moving the first point, I'm moving the second point. And you can see up at the top, we've got a kind of calculation for the formula of the distance between these 2 points. It's given by the difference of their x coordinate squared plus the difference of their y coordinate squared. So have a play around with that. You can pause the video and have a play around with that to kind of make sure that concept makes sense to you. Okay, so the first exercise that we've got here is that you're going to have to write a function, a Python function called distance that takes in 4 arguments. So it's going to take in x1, y1, x2, and y2, which corresponds to 2 points at positions x1, y1, and x2, y2. And then see if you can calculate the distance between these 2 points. So hopefully that makes sense. The formula that you're going to need to use is basically this one here. But you're going to have to basically write that in Python. So just as a little hint, you can take the square root of a number by doing np.square root of n. So for example, I can do np.square root of 25. That's going to be 5. or np.square root of 144, give me 12, etc. So we can take the square root of any number using this formula. And you can also square numbers like I showed you before. So 4 squared is 16, 10 squared is 100. So this star basically means to the power of. And you can do things in brackets or whatever. Cool. So your function here is, and if you can't remember exactly how functions work, you can always go back to one of our previous videos and have a look. But what we're doing here is we're defining a function called distance. It's going to take in 4 arguments, x1, y2, x1, y1, x2, y2, and then it's going to return something here. So you need to make sure that it's returning something at the end, just like this. So this is an example here of adding 2 numbers. That's not what you're going to do though. You're going to find the distance between these points. So give that a go, and then once you've written it, if you just run your cell like that, and then you can run this cell below, which is going to basically test your distance function to see if it's working fine. So if I run that, it's going to say it's not working because I haven't written it yet. So you're going to need to write that and test it here. Okay, so if you remember, the next step in our algorithm was to find the distance between our point that we want to predict, so that's our new point, and every single point that we already had on the graph. So here we were talking about x's and y's, but this could be anything. So in our example, this is going to be now weight, and this is going to be tail length, and we want to find the distance between those 2 things on the graph. So let's say that this is the data that we've collected. So here we've got a list of lists. So remember, square brackets means we have a list of things. And each item in the list is basically going to be another list. So we've got a list within a list. So it's a listception there. And the first item in each of these sublists is going to be the weight of that animal. This is going to be the tail length of that animal. And then this number here is going to indicate whether it's a dog or a cat. So a 1 is going to be a dog and a 0 is going to be a cat. So each one of these little lists is an animal. So that's the weight of the animal there, that's the tail length of the animal, and that's the type of animal that it is. So this is the data that we've already collected. And what I've written for you here is a function that goes through, that basically wants to predict, given a new weight and a new tail length, it wants to predict whether it's a dog or a cat. So I'm just going to explain this to you really quickly, and you can sort of pause the video and go through line by line and see if you can understand it. So we're going to start off with a list, an empty list called distances, which is basically going to hold the distance between our new point and each one of all of these points in the list. We're also going to create a list called animals, which is empty, and that's going to basically just hold the animal type for each one of our individuals in our data set. So we're doing a for loop here. So we're saying for individual in data, which means we're going to go for each one of these things, where individual will basically be each one of these as we loop through it. We're going to say the weight is individual 0. Now remember, 0 means the first item of a list. So weight is going to be individual 0. So weight is going to be this thing. And then tail length is going to be individual 1. So remember, 1 means the second element in a list, because we always start at 0. Tail length is going to be this. And the animal is going to be the third item in the list, a 1 or a 0. Okay. And then we're going to say d is going to be the distance. So that's going to be using your function here, which you just defined. D is going to be the distance between this weight, this tail length, and our new weight that we want to predict, and our new tail length that we want to predict. So this is basically going to tell us the distance between our new point here and our old point here, which we're going to do for each one in these lists, in this list. And then we're going to append d, this distance, onto our distances list. So that means we're just going to add it to the end of our distances list. And then we're going to add the animal, which is a 1 or a 0, based on whether it's a dog or a cat, onto our animals list. So our animals is basically going to end up being a list of, it's just going to be 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0. And our distances is going to be the distance between this new weight and between this new point with a weight here, new weight, and a tail length, new tail length, and each one of these. So we're going to have a distance for each one of these as well. Great. Now what we're doing here is we're doing nearest 5 is going to be np.argsort, the distances. So this is a new function, you won't have seen this before. But argsort is basically going to So now we've got this list of distances. It's going to sort all of these distances in ascending order, so smallest to largest. And it's going to basically sort the argument. So it's going to sort the index of these numbers. So let me explain what this means. So this is a little bit of a strange concept, perhaps. If we have a list that's basically 10, 4, 7, 2, 9, and if we did, so let's call that L, and if we did np.sort L, we're going to get that list sorted. So it's going to go 2, 4, 7, 9, 10. But if we go np.argsort L, it's not going to sort this list directly. It's going to basically tell us the index of this number basically in the original list. So instead of getting 2, 4, 7, 9, 10, we're going to get the index of 2, which was 0, 1, 2, 3. So it's going to be 3. Then the index of 4, which is 0, 1. The index of 7, which is 0, 1, 2. 9, which is 0, 1, 2, 3, 4. And 10, which is 0. So np.argsort L is going to give us 3, 1, 2, 4, 0. And there we go, 3, 1, 2, 4, 0. So that's what np.argsort is doing. And we're taking the 5 smallest ones because we're going to have all of these and of the distances, and we're going to just take the 5 smallest ones. So that's going to tell us basically which number, so are basically the shortest or the closest ones to this new point out of all of these in the list. Okay, so and then what we're doing here is we're saying we're going to set a new variable called count, which is 0. And then we're going to say for index in nearest 5. So basically for the nearest 5 animals, we're going to add animals index. So basically this is going to be a 0 or a 1 based on whether it's a dog or a cat. So it's basically saying for each the nearest 5 animals, if that animal is a dog, add 1 to the count. If it's a cat, don't add anything to the count. And that means if the count is less than 2.5, it's a cat. And if it's more than 2.5, it's a dog. So that's great. So now, hopefully, if you can run it on these functions here, it should be able to predict if we've got a new animal with a weight of 3 and a height and tail length of 26, is it a dog or a cat? If we've got a new animal with a weight of 32 and a tail length of 60, is it a dog or a cat? Now, this isn't going to work now. We're going to get an error because basically this function distance isn't returning anything yet. So you're going to need to write this function to return something, and then it should work. Okay, let's just get rid of that. Okay, so your second exercise is to use this function that's been created, so this one here, predict, to basically find out whether each of these animals is a dog or a cat, or predict whether each one of these animals is a dog or a cat. So first we've got an animal with a weight of 5.5 kilograms and a tail length of 42, blah, 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 blah. So for each one of these, basically call this function, predict, and see if it's a dog or a cat. Okay, so the next thing that we are going to think about is, well, what if, in addition to the weight and the tail length of each of these animals, we also had another variable? So, for example, what if we also had the paw width of this animal? In that case, our kind of method of plotting a distance on a 2D graph is no longer going to work, because we've now got more than just weight and tail length. We've now got another thing, which is going to be the paw width. So we're going to have to think of a new way of doing this. But actually, what we can do is just think about this kind of point being plotted on a 3D graph. So now let me show you what that looks like. So this is probably going to be something new to you. You probably haven't seen this before. But we could actually think of each one of these new points as being a location in 3D space. So this could be the X value, this could be the Y value, and this could be the Z value. And you can see here we've got this kind of 3D graph, which you can have a play with, where the kind of position in this direction is the weight, position in this direction is the tail length, and the position in this direction is the paw width. So we can basically plot all of our points again in this kind of 3D space. And then we can basically do the algorithm just exactly as before. We can just find, if we have a new point, which now has a new weight, tail length, and paw width, we can find the distance between that thing and each one of these, each one of the points, but now it's like a 3D distance. So you could think of it as like holding up 2 points in 3D space and measuring the distance between them with a ruler. But how do we calculate the distance between points in 3D space? Well, to answer that question, I want you to just have a look at this picture here. So this is a picture of a cuboid, I think it's called. And we asked the question, how do we know the distance between point H here and point B here? So this green line in this 3D cuboid. How do we know the distance of that line? Well, you might be able to see here, there's a kind of stood up right angled triangle, right? There's a kind of standing up right angled triangle here. So if we knew the length of this red line, and we know the length of this height, because it's given here, it's 4 centimeters. We know the length of this height. So if we knew the length of this red line, then we could calculate the length of the green line by saying it's going to be the square root of this red line squared plus the height squared. It's just Pythagoras, because you can just see this right angled triangle here. But we don't know the length of the red line, but we can work out the length of the red line by doing Pythagoras again, because we know this distance here, it's given as 3 centimeters, and we know this length here is 9 centimeters. So we can work out what this red line is, and then once we've worked out what the red line is, we can work out what the green line is. So so you can see here, I've just done a little thing which says the green line length is going to be the red line length squared plus 4 squared. But the red line length squared is going to be this squared plus this squared. No, 9 squared plus 3 squared. And that's the red line length squared. So basically you can say that the length of the green line squared is just going to be 9 squared plus 3 squared plus 4 squared. So it's actually really similar. So we're basically saying that Pythagoras, or the distance calculation in 3 dimensions, is just the same as in 2 dimensions, except you just add on the height as well. And as before with the points, if you have 2 points, so you've got one at x1, y1, z1, and another one at x2, y2, z2, then we can calculate the distance between them by doing their x separation squared, so that's this, plus their y separation squared, which is this, plus their z separation squared, which is this. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. The square root of all of that is going to be the distance. And again, as before, it doesn't matter if you do x1 minus x2 or x2 minus x1, it'll give you the same answer. You don't need to worry about that. Okay, so your third exercise here is to write that distance function again, except this one's called distance 3D. And this one is going to take in an x1, a y1 and a z1, and an x2 and a y2 and a z2. And it's going to calculate the distance between the point given by x1, y1, z1 and x2, y2, z2. So see if you can use this formula here, and it's going to be pretty similar to your function before, but see if you can work out how to find the distance in 3 dimensions between 2 points as a Python function. And once you've run that, again, you can run this little code here, which will test your function and see if you've got it right. Okay, so as a bonus exercise, and now this one is not going to be easy, but as a bonus exercise, what I've got here is I've basically copy and pasted my function from before. So now we're going to basically look, so given a new weight, a new tail length, and a new paw width, we want to predict whether it's a dog or cat. And as before, we've got this data block, except now we've got the weight, length, tail length, and paw width. And then we've got whether it's a dog or a cat. And I basically copied and pasted my function. I've just changed the name here to predict 3D and added paw width into the argument here. But other than that, it's all the same. So now see if you can go through this code and make a couple of small changes to make it work for a 3-dimensional problem. So you're going to have to change some things here, and you're going to have to change some things here. But if you can kind of go through this line by line and work out what the changes are that need to happen to make it work on this new data block and make it work with your new 3D function, then that would be amazing. And if you do have a go at that one, then you can test it running this cell here. And that is the end of this lesson. So thanks guys, and looking forward to seeing you next time.